And the higher we have this boundary, the less likely it's actually going to happen. All right, now what I'm assuming, if you're like me, most people are not going to want to do this. Most people are not going to want to do this out by hand every single time they have to do one of these calculations. All right, so let me go ahead and back to the whiteboard. All right, so here's what I'd actually recommend you do. So I'm going to go ahead and save this. And what I'm going to do is I want to show you how you do this calculation doing Excel. I call this version number 1. Okay, so I'm actually going to jump. I usually write this out when I'm actually in class because I don't have Excel easily. It's hard to go back and forth, but I actually do have Excel here, and I can pretty easily show it. So I'm going to actually bring up an Excel sheet, and I'll share it so we can actually walk through. This together, and you can see how I would actually run this. I'm going to make it pretty big. I mean, really big. Okay. All right. And what I'll do is I'll actually show you the formula. So I'll type the formula in here, but I'll use formula text so you can actually see what I'm actually entering. Now, one of the things I like to do is I actually like to sort of keep track of my value. So I know that N was 600. So I'm going to go ahead and put that I'll use column A as my labels and column B as my values. And since I'm going to use these as labels, I'm going to center this and make it bold. So kind of center, make it bold, and I'll sort of give it a different color so it kind of stands out a bit. All right, so N is 600. P was, and it's technically in this case, maybe I should say P star. So P star in this case was 60%. So I'll just get 1 minus P. It's just I need it, so I'll just calculate it ahead of time. So this is what I entered in here. So the formula that was entered here, if I actually click on this, it's just 1 minus B2. And here's the formula that's actually showing up for that. All right, so let's actually get the mean. I know what the mean of the distribution is. That's just my P star. So that's just the value B2. Now, when you can break apart the formula so you don't, like it is possible to write this out as one long formula in one Excel cell, but I find, so I want to get the variance. So the variance is, well, it's quite literally these values all multiplied together. N, the P star times 1 minus P star divided by the sample size. So that's the formula for the variance. And the standard deviation, or in this case, technically the standard error, because remember the standard deviation of the sampling distribution is called the standard error. You'll see this SE a lot. That's just the square root of this value. So now what I've done by doing this, watch, if I come up here and I change my sample and say, oh, actually, I'm not interested in 600 anymore. Now I'm actually interested in a sample of size 500. Everything updates for me automatically. Or let's say maybe my sample's not 60%, but maybe it's 55%. Again, everything updates automatically. So that's what I mean by quote unquote using Excel efficiently. As you keep working in Excel, so let's say if this were a messier number, if you ever have to write this number, I can always refer to it as cell B7. That's the other advantage of using Excel. That's the other aspect that keeps things efficient. So I'm going to highlight these two cells here only because these are the ones we changed. If I change these two, everything else updates. So the next thing I want to do then is, I know that I want to find the lower 2.5%. Okay. And if I want the lower 2.5%, it means I want the upper 97.5%. So there's technically a formula in here as well. So I entered this value. This one updated automatically. Again, this is just 1 minus. I'll put the formula text for this one here below it. So that's what's actually entered there, all right? But now the formula here, this is probably the messiest of all the formulas. This is going to be equals norm inv. I'll take this A9, and I'm not going to say B5. I want it to go to B5 to get the mean, but I'm going to say $5. What does the $sign do? What does that $sign do? Does anyone know? Anyone remember? Exactly right. This is always going to go back to row 5. So if I copy this into the cell below, A9 is going to change, and it's going to say, oh, I'm now in this row, so I should look in A10. But the 5 will always remain fixed. And I'm going to do the same thing for $7 to get my standard deviation. So here's the formula text, okay? And now watch when I copy this down, that's exactly what happens. It still stays looking in B5 and B7. And I do believe these were the values we had, 56.1, 63.9. Okay. And again, the advantage was that I was able here to copy B9 into cell B10. And because of what we call absolute referencing, it updated automatically. Okay. All right, so this is version 1 of the so this is version 1. Let's look at version number 2 now. So version number 2, I want to this one's a little, I don't like the way I set this one up. So I'm going to actually go ahead and redo this a little bit. I'm actually going to put in the value 95% here. And then in this cell, I'm not going to have this here. I'm actually going to have it. So then this is going to be 1 minus A9 divided by 2. And then this is going to be A9 plus A10. Okay. This is actually, I think this is probably the most efficient way. It pretty much, I don't want to say that if you use what I just typed, you will never have to write this out again. But if you use what I just typed, you'll never have to write this out again. So the point is, if you change these 3 values to whatever your current problem is, this is always going to update to give you the range of usual values. So instead, if we had been looking for 98%, it updates automatically. If I'd been looking for the middle 50%, which is a bit extreme, but regardless of what I put in here, it is all going to update automatically. So if there's 95 in here, there's 5% left over total. Yep. So that means this is half of that 5%, or 2.5, and this is half of the 2. This is the other half, 2.5. So I have 2.5 here. So if I'm looking for that boundary, I want the lower 2.5 from everything else. And then up here, if I want the upper 2.5, Excel thinks about it this way. It doesn't think about what's to the right. It thinks what's to the left. So if there's 2.5 to the right, that means there's 97.5 to the left. So if I'm looking for this boundary, 2.5 to the left, this boundary, 97.5 to the left. Let's say this had been 98, and it would be 1 and 1. So that would be 1%, and this would be 99%. So let me move that. So what I'm going to do is, how about I do this? I'm going to zoom this out a little bit. All right, I'll put those formulas down here. Okay, so these are, I'll color code them. This one is, let's make this one be light yellow. And I'll make this one sort of be like light green. All right, I want to do one more problem, and time-wise, I think we're good for it. So let's do another problem together. And here is the situation. Numbers, I'm looking at my two sheets, and somehow, for some reason, the numbers are changed on one set of notes than they are on the other. I'm not sure how I missed that. So I'm going to change this on the fly, but I think I could do it without screwing up too badly. All right, let me go back to the whiteboard. All right, so we saw using Excel efficiently version 1. We also saw version 2 where I changed it a little bit. All right, so now let's do the following. Here's the scenario. So I'll clear this. All right, so let's work on an example here. Okay. I'm going to write these numbers in. I'm going to use different colors. So I'm going to do it like this. Okay. So here's the scenario that we're working on. All right. So at some time previously, okay, so let's say at time number 1, okay, this is sometime previously, okay, the particular person in office had a 60% approval rating. All right, so someone's working in government, they have a 60% approval rating at time 1, all right? And what we have is we have at time 2, we have collected information at time 2, and so we want to ask a couple questions about how things may or may not have changed over time. All right, so here's the scenario. We have, I'm going to work with this idea that the approval rating is the same. So we're assuming the approval rating, the population proportion of excess, we'll assume it was what it was before, which is 60%. Now it's kind of strange what our sample size is, but it's what we've got. We've collected a sample of size of 57. Sample size of n equals 877 individuals. So we have a sample size of 877. And let's say we want to calculate the middlemost. Let's just because I just want to do it with a different number, let's do the middlemost 90. We're going to say the middlemost 96% is going to be what we're going to take to be usual versus unusual. So the middlemost 96% of the sample proportions. That's what we're going to define as usual and unusual. Okay. So what I would like to do is I would like to get an estimate of the location of the middlemost 96% of sample proportions if the proportion is 60% for the population and we take samples of size 87. Right? So I'm going to just jump up. Let's take these values and put them in Excel, because if I did this correctly, Excel should give us everything we need for this. All right, so here is Excel, the Excel sheet. So let's punch in the numbers. So our sample size was 877, is that right? N star is still 60%, but now we're looking at 90. We're saying usual is 96%. Okay. So if I take these values, I'm gonna punch these values into my R plot. So get rid of this one. So my mean is at 60%. I need a standard deviation of well, as a percentage, it's 1.6. I'll do 1.654. That should work. 1.654 should work. I want it to go from 56.6025. 56.6025 up to 63.39, 63.3975. All right, so if I plot this, fingers crossed. All right, so this is the plot. So our standard deviations are kind of spread out in a strange way here, which is why some of so the numbers were too messy that so it didn't actually generate a value here for us on this one. Probably if I actually can probably reduce it by a decimal place, it'll probably be just fine. Yeah, that's still readable. Okay. So these are the values that we're considering usual. So the middlemost 96%, so this lower 2% and upper 2% would be considered unusual results. All right. What are those values? Well, it's 56.6% down here and 63.4% up here with rounding. Okay, so taking those values, taking these information, let's go ahead and record that on the whiteboard. So the values we just found for usual and unusual are, so let's record those in purple. All right. So we just found that the values of 56.65, sorry, no, it was 56.6% up to 63.4%. That's the range, that's using interval notation, that's the location of the middlemost 96% of sample proportions. So if we take this as our definition of usual, so this is what we would expect if we have a usual sample and the population proportion was 60%. Okay. Now, here's the problem though. Here's the problem. Well, it's not a problem, but here's reality. So so this was the information we had at time 1. The problem is we're now looking at time 2. So we're now looking at time 2. Okay. And we just took a sample of 877 individuals and P hat is 50%, not, well, no, it's 50%. Well, it's not exact, it can't be perfectly 50%, but within rounding, it's 50%. Okay, so here's the question then. And this is going to tie, this essentially is going to be your end of class question. So what do you think? Okay, so what do you think? Has the approval rating changed? And if so, and either way, why or why not? If this is the range of usual values, if the percentage is 60%, and this is the result of the sample we just had, what do you think? Has this particular government official's approval rating changed or not? Okay, so this one's a little more open-ended. This is a little more open-ended end of class question, but I'll leave it there.